Okay, so we have discussed Newton's third law last time. We also discussed the difference between action and reaction and balance forces. Okay, so now let's first use this two very short questions to test our understanding of action and reaction and the difference between them and the balance forces. Okay, so take a look at the question on slide 11, the same PowerPoint. You're towing your trailer with your car on I-40 at a constant velocity. So I want you to tell me which of the following are action and reaction forces. Which pair is the action and reaction pair? Okay, so take a look at these five answers. Which one is the right answer? Okay, think about it. All right, so the right answer is the pulling force from the car on the trailer and the pulling force from the trailer on the car. Okay, because action and reaction forces forces between A and B. The force from A, object A on B, and the force from object B on A. Okay, so all you need to do, if you want to find action and reaction forces, all you need to do is just switch A and B. Okay, you don't even need to know the detail of the motion. Okay, you don't even need to know if they are at rest or moving with a constant velocity or acceleration. If you tell me they're the force from A on B, the reaction force, I don't even need to know any detail about these two objects. I would say the reaction force is just going to be the force from B on A. And these two forces, they're always going to be equal and opposite. Okay? So that's going to be B, the pulling force from the car on the trailer. At the same time, there's a pulling force from the trailer on the car. Action and reaction. Okay. Now let's take a look at the next one. So the same situation, you're still towing your trailer on I-40 at a constant velocity. Now I want to ask you which force balances the force, the pulling force from the car on the trailer. Okay. Now again, take a look at these five answers. Which one is the right answer? Okay. Which force balances the pulling force from the car on the trailer? Okay. So now we're talking about balance forces. We're not talking about action and reaction. Okay, which one is your answer? The right answer is D, the friction force from the ground on the trailer. Okay, why? If you want to figure out the friction, the balance force, you definitely need to know all the forces on this object you are talking about. You need to know the details. Okay, so this is different from action and reaction. So if I need to figure out which force balances the pulling force from the car on the trailer, so this is a force on the trailer, okay, from something else, but it's on the trailer. So I'm going to draw a free body diagram on the trailer, okay, because I need to figure out another force on the trailer that balances this force, okay. So let's draw. So this is the trailer. Okay, this is the trailer. How many forces on the trailer? Okay, of course, if I want to draw all the forces, gravity is on it. Okay, mg, and then of course there's a normal force from the ground, and I know that these two forces, they're gonna balance each other, right? So I can call these two forces balance forces. Okay, no question. Now, any other force on this trailer? Well, of course, there's a car, the force from the car on the trailer. Okay? So, is there another force on this trailer in horizontal direction? Of course, there's a friction. We're going to discuss friction in detail in a little bit. There's a friction force on the trailer from the ground, right? And then these two forces, they must also balance each other. Why? Because the problem says the trailer and the car are moving with constant velocity, right? Anything moving at a constant velocity, from Newton's first law, all the forces must balance out, right? The net force must be zero. So if these two forces cancel out, in y direction, then these two forces, they must cancel out in x direction. Okay, so, and these two forces, they are on the trailer, so they are balanced forces. Okay, then what about the force from the trailer on the car? You don't draw that force on the trailer, right? If I'm interested in the car, this is a car, I want to draw all the forces on the car, I will draw this force. You see, there's a force from the trailer on the car. These two forces, they are action and reaction. We just saw that in the previous question. But you never say they cancel. They don't cancel because they act on two different objects, right? Remember the metaphor I gave you last time, right? If Newton transfers $200 to his girlfriend, these two transactions, they are in two different accounts. You never see these two transactions in one account, right? So you shouldn't say they cancel. They never cancel because they are on different objects, right? These two forces, a lot of people tend to make that mistake because they have learned action and reaction are always equal and opposite. So if I have two forces equal and opposite, they should cancel. But that's when these two forces are on the same object, right? These two forces, the force from the car on the trailer and the friction force from the ground on the trailer, they are both on the trailer. They're both in x direction. And then if the problem says this trailer is moving at a constant velocity, these two forces must balance out, must cancel out each other exactly, okay, in order to make this trailer moving at a constant velocity. These two forces, they never cancel. They are action, reaction, but they act on two different objects. You never add them together. You never subtract them together. You never put them in the same equation because they are on different objects. So you never say action and reaction forces cancel. You never say that because they don't. They act on different objects. Okay? So if you want to figure out balance forces, you're going to draw all the forces on the object. You also need to use the motion of this object to help you figure it out, right? For example, if I change this question for these two parts, say you're towing a trailer with your car on I-40 at a constant acceleration, okay? At a constant acceleration. Take a look at the previous part. So is this still true? The pulling force from the car on the trailer and the pulling force from the trailer on the car, are they still action and reaction forces if the trailer and the car are moving at a constant acceleration? Yes, they're still true, right? Because this is always true. I don't need to know the detail of the motion, the details of these two objects. If there's a force from A on B, there must be a force from B on A, okay, equal and opposite, simultaneously. But if you tell me that the car and the trailer are moving at a constant velocity, I'm not going to say these two forces balance each other, right? They're not going to be balanced forces because if there's an acceleration on the car, then obviously this guy, the force from the car on the trailer is going to be greater than the friction force from the ground on the trailer. So that's going to change my answer, right? So you see that if you want to figure out balance forces, you need the details, okay? You need to know the detail of the motion, the details of this object. Action and reaction, no. You tell me these two objects, I can give you action and reaction. It's just going to be switching A and B. That's action and reaction. Okay, so I hope these two questions help you understand the difference between action and reaction forces and balance forces. Okay. Now let's take a look at the applications of Newton's third law. We use Newton's third law every day, right? We use Newton's laws every day, okay? It's just a lot of people don't realize, don't call them laws. Okay, for example, when if you skateboard or if you run, okay, so say if you run this way, okay, you're gonna push the ground in this direction, right? If you want to skateboard this way, again, you're going to push the ground this way using 1 foot, right? Because you know that by doing that, the ground is going to give you a force in the opposite direction, which is the reaction force. That's the force you need to go in this direction, right? You never push the ground in this direction if you want to go that direction. You know that you're going to go the opposite direction if you do that, right? So we know that we use Newton's third law every day, right? It's a lot of people just don't call them laws, okay? Now think about swimming. Right, when you swim, okay, you're going to push water in which direction? You're going to push water backwards, right? If I want to go that way, I'm going to push water really hard in this way. Why? Because I want to get the reaction force from the water on myself in the opposite direction. And I definitely know that, right? So that's why every time I swim, I'm going to do it this way. I'm not going to do it this way. If I do it this way, I know I'm going to go backwards, right? Everyone knows that. So we use Newton's laws every day. We use Newton's laws every day. And then also in swimming, think about flip turns, right? How do you make a flip turn? You're going to kick the ball very hard. You kick the ball so hard in this way, and then you know the ball is going to give you a reaction force in the opposite direction, which is going to help you make the turn, because you need the force to make the turn, okay? So we use Newton's laws every day. Every day, okay. Okay, so that's the applications. You can see applications of Newton's laws every day around us, right? Because Newton's laws is all about mechanics, all about motion and forces, okay. The next thing we want to do is this. So we want to, first of all, we want to clarify something again. A lot of people are confused about is that if you have many objects together, okay, and you push this object using 1 force, okay, so this is a confusion some people may have. Like I push all these objects with 1 force, but only on the first object. And then is that force on, say, the 4th object on the right? If I want to figure out all the forces on this object, do I need to draw that force on the 4th object? That's one of the confusion some people may have, okay? So another thing we want to figure out is that does Newton's third law agree with Newton's second law? Do these two laws agree, okay? So what we're going to do is that we're going to do some algebra. We're going to use an example. We're going to draw some general conclusions using symbols. Again, we're dealing with symbols. We will confirm Newton's second law and Newton's third law. They agree with each other. Okay, so how do we do that? Let's take a look at this question. Okay, the 2 blocks M1 and M2 under force F. Okay, so that's the example we want to discuss. So to make things easier, let's assume the surface is totally frictionless, okay? Let's not worry about friction for the moment. So there are 2 blocks here, okay? They're in contact, and then I call them M1 and M2, okay? So if I apply a constant force on M1 and pushing this whole system to the right, so if the friction is negligible, of course, these 2 objects, they're going to start to move in that direction, and then they're going to get faster and faster because nothing is stopping them, okay? So we want to find the force between them, the force between from M1 on M2 and then the force from M2 on M1. That's what we want to find. But first of all, I want you to find the acceleration of M1 and M2 as a system, okay? So how do I find the acceleration of M1 and M2? Of course, they will have the same acceleration, right? Because I know that if I do this experiment, I push these 2 objects, they're going to move as a system, as one object to the right, okay? So they will have the same velocity acceleration. They will always travel the same distance. Then how do I find the acceleration of M1 and M2, okay? So this part is actually, the first part is an easy one, right? So I'm just going to consider both of them as one object. So this object I call m1 plus m2, right? So this object has a total mass m1 plus m2. How do I find the acceleration of this object if I have a force F on this system? Well, I can use Newton's second law, right? Because Newton's second law connects force and acceleration, okay? So if I use Newton's second law, so I would draw all the forces on this guy, right? So gravity is down, so that's m1 plus m2 g, right? Mass times 9.8. Now normal force up. Okay, so again, I know that these two forces, in y direction, they're going to cancel out exactly because the system is not moving in this direction. So no velocity, no acceleration in y direction, no net force in y direction. So obviously, these two forces cancel. Okay. Now in x direction, how many forces in the x direction? Only this force is on in x direction, right? So I can apply Newton's second law in x direction, which is that force in x direction divided by the total mass of this object, right? So the net force in x direction is just going to be the F given in the problem, okay? So this is going to be F from the problem. What is the mass of this system? If I consider these two objects as a system, as one object, this is going to be the mass of this object, right? Okay, so that's going to be my answer, right? Because I have these three symbols from the problem: F, M, M1, M2. Okay, so that's going to be my answer. Okay, so this the first part is straightforward. Now let's take a look at the second part. Okay, the second part, I want you to find the magnitude of the force from M1 on M2. From M1 on M2. So now I'm trying to find a force on M2. Okay, I should draw a forward diagram of M1 or M2. Think about it. I want to find a force from M1 on M2. I'm interested in a force on M2. I should draw a forward diagram of M2. Okay, so that's what I'm going to do now. Let's draw a forward diagram of M2. So this is a forward diagram of M2. I'm going to isolate M2 and draw all the forces on M2. Again, the first force I always draw, okay, if I'm drawing a forward diagram, it's always gravity, because gravity is always there, right? And I don't want to miss that, okay? So M2 down, right? Of course, M2 has a normal force, right? If I call it Fn2, and then M1 is pushing M2, right? So, and that's the force I want to find. So that's 1 on 2, M1 on M2, right? And there's no friction, so we don't need to draw any friction on M2. So some people, they would ask, do I draw F1 on M2, right? Is M1 on M2, okay, in this case? No, you don't. This F is only on M1, okay? But some people may say that, well, the reason M2 moves is because F is pushing both of them, right? Yes, F is pushing both of them, but what M2 feels, think about that. If you're M2, you only feel that M1 is pushing me, right? M2 doesn't know what is pushing M1, right? M2 is only in direct contact with M2. M2 is only in direct contact with M1. It only feels the force from M1, right? Whatever is happening on M1, M2 doesn't need to know. M2 doesn't know, right? If you feel this doesn't convince you, I'm going to give you an extreme case, right? Think about it like not just two blocks, like, you know, 100 blocks, okay, lined up, okay, one next to another. So this is the first, this is second, third, etc., and this is 99th, this is 100. And then if I use a very large force to push all of them to the right, Does this block on the right, okay, the 100th block, feel this force? Of course it doesn't, right? There's so many blocks, okay? This guy doesn't even know how many blocks are to the left, okay, on his left. He doesn't know, right? This guy only feels the force, okay? If I draw the force horizontally on this block, it only feels the force from the 99th block on it. It doesn't even know how many blocks are on the left. It doesn't even need to know, right? What determines its motion? It's just going to be the direct force from the block next to it, right? It doesn't even know what's going on here, okay? You can have like 100, 1,000 blocks here, okay? This force is not directly on this guy, and it's not directly on the second block or the third block. No, it's only directly on the first block. So you don't draw that force. You don't draw that force directly on any of these guys except the first one, okay? So when you draw a Ferber diagram of all the other blocks other than the first one, you don't draw this force, okay? Does this force have any effect on other blocks? Yes, we're going to see what the effect is, okay? But when you draw the Ferber diagram, you don't draw that force on any of these blocks, okay, except the first one, which is in direct contact with this force. So in this case, this is going to be the free body diagram of M2, okay? Complete free body diagram, all the forces on M2. Now I'm trying to find this value, right? I don't have the number, but I'm just going to use all the symbols. I'm just going to use all the symbols, right? So again, I would say everyone is going to agree these two forces, they're going to cancel out exactly, right? The normal force is going to be equal to gravity in y direction because these are the only two forces in y direction, and then there's no movement in y direction, right? So then I can set up Newton's second law in x direction to find this force I need, right? But when you set up Newton's second law, remember, a lot of people will say F equals ma. But when you set it up, you actually get this. The net force on the M2, it's going to be equal to, in this case is the x direction, right? It's going to be equal to M2 times A2x. That's Newton's second law. Don't forget the net force, okay? So now you see that if you plug, so this M2 is a symbol given the problem, so that's something the problem assumes that I already know that, okay? What about the acceleration of the M2 in x direction? Well, because M1 and M2, they have the same acceleration, and that is the acceleration I just found here, right? Because this is going to be equal to A1x and A2x for sure, because that's the acceleration of the system. They will move with the same acceleration. That's what I figured, right? So now you see that I can plug this in. So I will get an expression M2 times that F divided by, I'm working with all the symbols, okay? A lot of people, they have difficulties working with symbols. That's something you need to work on, okay? Because we will work with symbols, okay? In this class, in some of the problems, if we want to draw a general conclusion, we don't want just to plug numbers for a specific case. Some people will say, oh, that's going to be my answer, but you should be careful. When you do mass times acceleration, you get a force. That's the net force. That's not always the force the problem asks. If the problem says explicitly, find the net force on M2, that's your answer. You can stop here. But does the problem say find the magnitude of the net force on M2? No. This part says find the magnitude of the force from F1 on M2. So you actually need to use this force to connect this force to the force from M1 on M2. And in this problem, in this part, it's easy because if I show you this Ferber diagram and I ask you, what is the net force on M2? You would just tell me, well, that's easy. Normal force and gravity cancel. the net force on M2 is just gonna be the force from 1 on 2 from this free body diagram, right? Okay, so the relation between the net force and the force from 1 on 2, which is the force the problem asks me to find, it's the same. They are the same value, okay? But in principle, they're not always the same force, okay? But in this case, if I find the net force using these symbols, and then I also realize that the net force is just gonna be the force from 1 on 2, so my answer, okay, for this part is gonna be this, because the net force is just gonna be equal to the force from 1 on 2, and then so I'm just gonna use this value, this expression. So that's going to be my answer, okay? So now we're going to move on to the last part. Find the magnitude of the force from M2 on M1, okay? So now we're finding the force from M2 on M1 again using Newton's second law. We still want to use Newton's second law. We're going to see if our answers agree with Newton's third law. That's what we're doing here. Okay, I'm trying to find a force from M2 on M1 in this part, right? So I'm going to draw a Fourier diagram of M1. I'm not going to draw a Fourier diagram of M2 because I'm trying to find a force on M1. Doesn't matter which force, where this force comes from, but I'm trying to find a force on M1. I'm going to draw a Fourier diagram of M1. Okay, so that's what I'm going to do here. Let's draw a Fourier diagram of M1. So I'm going to draw it here. M1, if I draw a Fourier diagram, so again, gravity is down, M1G, okay, for sure. That's always the first force I draw if I draw a Fourier diagram. Normal force up, if I call that normal force 1, okay. And then the F is on it. For sure, right? So now the F is on it, right? Because this F is directly on M1. So I should draw this F on this M1. Then M2 has a force on M1, right? And in the opposite direction. So that's the force I'm trying to find, F2 on 1. Okay? So now I want to find this force. Again, I'm gonna do what I just did. Okay, I want to use Newton's second law because Newton's second law connects forces and acceleration. So if I apply Newton's second law, so in y direction, okay, I don't need to do that because I realize that these two forces, they can cancel out exactly. So no net force in y direction, no acceleration in y direction, okay? In x direction, so I would write this, right? So if I apply Newton's second law and on M1, I should get this. Net force on M1 in x direction should be equal to M1 times A1x, right? This is Newton's second law. Again, you should know that when you use Newton's second law, you always get the net force. Right? You don't get a single force out of this equation. Now, again, I will do this. So what is A1? So M1, I leave it here. What is A1x? Well, that's going to still be the answer I found in the first part. Okay, so I'm going to plug it in. Symbols, that's fine. I'm working with symbols. I want to find a general expression with symbols. So that's going to be the net force on M1. Okay, so again, a lot of people, they would just stop here. They would say, that's my answer, because I just did mass times acceleration. That's going to be the force. Read the question carefully. What is the question? Find the magnitude of the force from M2 on M1. Does the problem say find the net force on M1? No, it doesn't. Okay, so what you just found by using Newton's second law, you only found the net force on M1. You actually didn't find the force the problem asks you to find. Okay, you didn't. Okay, so again, like what we did with M2, you're gonna find the relation between the net force on M1 and the force you want to find. Okay, so in this case, they're not gonna be equal because there are now two forces on M1. So if I give you this Hilbert diagram of M1, I want you to write down the net force for me on M1. How would you write it? How do you use these four forces to write the net force on M1 for me? You would say, well, okay, y direction, no net force, cancel out. X direction, what is the net force? Well, obviously it's going to be this F minus the F from the force from 2 on 1, right? So that's going to be how I find the net force on M1 using the Hilbert diagram. It's going to be whatever the F is minus the F2 on 1. So this is different than M2, right? What we figured out for M2 is that once I find the net force on M2, I realized that on M2 in X direction there's only one force on it, which is the force from 1 on 2. So in that case, the net force on M2 is going to just be equal to the force from 1 on 2, which is the force I was trying to find in that part. So that is just going to be equal to the net force. So that's why I can just write F1 on 2 equals the net force on X on 1 in X direction, right? So that's going to be 2 in X direction. So it's going to be equal to this value I found. And this part, they are not equal. Look at this equation we just realized, right? What is the relation between the net force on 1 in X direction and the force from 2 on 1? They're not equal because there are two forces on this M1 in X direction. This is going to be the relation between these two forces, three forces, right? So if I apply Newton's second law, I only found this, right? But the problem asked me to find this. So how do you use this value? You can go ahead and use this, right? But this is not your answer, remember. This is not your answer. This is not your answer. How do you use this value to find this number? Okay? So look at these three symbols here. I have an answer for this guy. I have this value from the problem. Okay, it's a symbol. How do I find the third guy in this equation? Well, I would just rearrange this equation, right? It's like x equals y minus z. How do you find z? I would just rearrange this equation and then find z on the left-hand side or right-hand side. Put everything else on the other side, right? So that's what I'm going to do. You have to finish this step so that you can find the force from 2 on 1. And because that's what the problem is asking you to find. The problem doesn't ask you to find the force, the net force on M1, right? All right, so you're going to rearrange this equation, get an expression for F2 on M1, the force from 2 on 1. Then you're going to plug in this expression. You can find the expression for F2 on M1. Okay, so that's what I want you to do. Now you can pause the video, finish the algebra. Okay? All right, so let's see. First of all, I'm going to rearrange this equation, right? If you rearrange this equation, forget about this, these three guys, right? It's x equals y minus z. How do you find z? Well, I would do this, right? So z is going to be equal to y minus x. Right? So that's how I'm going to rearrange this equation. Whatever these three symbols are, that's how I'm going to rearrange that to get this guy. Now you see that I can plug this. So F is known, is from the problem. I found this net force on M1 using Newton's second law. Now I'm going to plug it in. So now you see that if the problem gives me the numbers I need, like F, what is F? Like 10 newtons. What is M1? 2 kilograms. What is M2? 3 kilograms. Okay, now I can put numbers in and then get the answer. right? But now I don't have my number, so this would just be my final answer, okay? But now we want to, you know, rearrange it, manipulate a little bit, okay, to simplify it, okay? So how do I simplify this expression? So I realized that the second term is just going to be f times something, right? So as the second term is just going to be f times m divided by m1 plus m2. So this is totally math. This is totally math. I'm doing math with these symbols. So I can factor out this f, right? To make it a little bit nicer, I can factor out this f. So what do I get? I get 1 minus m1 over m1 plus m2. So I can also make this thing a little bit simpler by writing this one as m1 plus m2 divided by m1 plus m2. Why do I do this? You're going to see why I want to do this. If you do this, you see that these two guys, they're going to have the same denominator. If they have the same denominator, you can just subtract these two numerators, right? You can combine them. So what do you get at the end? So at the end, you will get this 2 on 1. It's going to be f. Now I'm going to have m1 plus m2 at the bottom because they have the same denominator, so I can just subtract these two numerators. I get m1 plus m2 minus m1. What do you get at the top? You just get m2. So why are we doing this? Okay, a lot of people, they may be confused, like what are we doing with all these symbols? This is the value of the force from 2 on 1. What is the force we got in the previous part? The force from 1 on 2. Okay, the force from 1 on 2 is this. So let's copy it down here. The force from 1 on 2 we found in the previous part is m2 times f divided by m1 plus m2. Now compare these two expressions. They are exactly the same. So we started from Newton's second law. Okay, we actually derived the expression of the force between m1 and m2 using m1 and using m2, and isolated them, and then find the same the force from 2 on 1 using Newton's second law. Find the force from 1 on 2 also using Newton's second law, and then we confirm that the answer is going to agree with Newton's third law, because these two numbers, they're going to be the same, so equal and opposite. Newton's second law and Newton's third law, they are consistent. So Newton's laws of motion, okay, is a complete and consistent theory, okay? So that's what we are doing in this question, okay? So I'm gonna stop here for this video.